Hi everyone, we're going to be talking today about how to graph sine and cosine as actual functions. Um, as you recall, we defined the cosine to be the x value of a point on the unit circle, the cosine specifically of the angle that creates that point. So for example here, when we're 45 degrees around the unit circle, that brings us to this point on the unit circle, and we say that the cosine of that angle 45 degrees, or pi over 4 radians, must equal square root 2 over 2. And similarly, we would say that the sine of 45 degrees equals square root 2 over 2, because you can see that the x value and the y value here are the same, right? So, but the x value is defined to be the cosine, and the y value is defined to be the sine. So if we just make a table of values for our sine and cosine functions as we go from 0 to pi, we can see the general structure of our function starting to emerge. So for example here, when x is 0, or when our input, I should say, is 0, we can really think of these x's as thetas. They're unknown angles, right? So when our theta is 0, our y value here is 0, right? And so that's our sine. And our x value is 1, so that's our cosine. So I can fill in here 0 for the sine and 1 for the cosine, right? Then at pi over 6, that's right here. That's the same as 30 degrees. So when our angle theta is 30 degrees, or pi over 6, then we have a sine value of 1/2, which I'll fill in here. We'll do the cosine in a moment. At pi over 4 radians, which is here, our y value is root 2 over 2, so our sine of pi over 4 is square root of 2 over 2. Notice, by the way, this is a little bit more than 1/2, because keep in mind, this is the height on the unit circle, right? And so it's pretty easy to see that this point is higher up off the x-axis than this point. So this is like 1/2 here, whereas this is the square root of 2 over 2. So going back here, get rid of that greater than sign. So our value here is increasing. Pi over 3 follows that trend with root 3 over 2 as the y value at that point. You can see that here. Root 3 over 2 is our y value. And you can see, again, that's a little bit bigger than root 2 over 2. Pi over 2, we've reached the very highest point on the circle. So this height here is just 1, which is greater than all the ones we've had so far. And then you can see, as we go symmetrically around the circle, we go back to the old values we had. So here are the ones we've already reached. You can see over there at 2 pi over 3 radians, or 120 degrees, our height is root 3 over 2 again. Then we have root 2 over 2 again, then 1/2, and then finally 0. So I'll copy those down. Root 3 over 2, root 2 over 2, 1/2, and 0. Now, the interesting thing here is let's track, instead of our y values, which are our sine values, let's track the x values of these points, which, as we know, are the cosine of theta. Well, we start off at 1, like I said, but then the next three are root 3 over 2, root 2 over 2, and 1/2, all familiar numbers from what we just did. In fact, it's looking very much like this, right? If we just copy this over to here, which would imply our next thing is 0, our next value is 0, which indeed it is. If we look up here at pi over 2, our x value is 0. And if this trend continues, in fact, because next up we're going to have 1/2 root 2 over 2 and root 3 over 2. Look, our x value here is, although they're in the negatives because we're on the left side of the y-axis, negative 1/2, negative root 2 over 2, and negative root 3 over 2. And then finally, we're going to get down to -1. Now, what this would look like on graphs is this. If this is our sine of theta, this is you can think of this as like a theta axis, whereas this is still like a y-axis, y equals sine theta. Or you could think of this as the sine of theta axis if you prefer for now. As we go from 0 to pi here there's pi over 2. We'll have our 3 points in between, which I won't label, but they're the same 3 points that we have here. What essentially we end up getting is this. We smoothly transition up from 0 to 1 on the sine at pi over 2, and then we smoothly transition back down to pi. Now over here on the cosine graph, if this is our cosine theta axis and this is a theta axis, as we go from 0 to pi, here's pi over 2, and then again I'll just put the 3 points in between. We start at a value of 1, then we curve smoothly down to 0 at pi over 2, and then we curve down to -1 over here. Now, this worksheet only had us graph half a period of each of them. The full version of the sine actually looks like this, and it goes over to 2 pi. And the full version of the cosine is like a mirror image of what we've just done. So that's what sine and cosine look like on the graphs. If you put them into a graphing calculator or something, you'll see something like this, except it will continue forever in both directions, right? These will keep going. These are both like wave functions, you could think of them as. Now, that's just to give you a little bit of a taste of what these functions actually look like. Now, if we go over here, these are going to rely on some new information for us. So we need to know the standard form of the sine and cosine graph. The standard form of the sine and cosine graph, they work the same way, so I'm going to give it to you for the sine, but if you literally replace sin with cos, this is the standard form of cosine as well. A letter A, or a number A, times the sine of bx minus c plus d. This is what's called the standard form. So these numbers A, B, C, and D are all important numbers in terms of determining the properties of the graph of this function. Now, some of these have names, and some of them are not going to have direct names. So, for example, the A is known as the amplitude. Technically speaking, actually, I'd even say the absolute value of A is called the amplitude. Like, if A is 5, we'd say the amplitude is 5. If A is -5, we'd still say that the amplitude is 5. You don't really have to remember that absolute value thing. Just remember we always talk about the amplitude as a positive number. Amplitude represents the distance that the function goes from the middle of the function. We'll talk about that more in a second. So I'm going to write down the rest of these definitions and then we'll talk about what they mean. 2 pi divided by b is called the period. I cannot stress enough that b is not called the period. Only 2 pi divided by b gives you the period. So for example here, pi over 4, I would actually call this the frequency, though that's not a vocab word you need to know for this class. Pi over 4 is not the period of this function. We'll do 2 pi divided by pi over 4, and that will give us the period of this. Again, I'll tell you what that means in just a moment once I've finished writing all of these. C over b is called the phase shift, and d is called the midline. So, most of this is actually just coming directly from function transformations, like amplitude is just a vertical dilation, midline is just a vertical shift, and period and phase shift are a little more complicated, but they're related to both a horizontal shift and a horizontal dilation. But here's what it generally looks like on a sine or cosine curve, but we're going to use sine for this example. the midline of a sine curve is not actually part of its graph, but it's an imaginary horizontal line that the sine function never strays far from. It's always right in the middle of the sine function, right? It's the you can think it's the middle y value that the sine function takes on. So that's called the midline. Now, the distance from, and actually I could do some color coding here. We'll say the midline is, oh, no, it's not letting, it's not, oh, it's just being stupid. Nope, it's being very stupid. Okay, I'm not going to do color coding. The midline here is the y value at which this horizontal line shows up. Now, the distance between the top of the function and the midline, that's the amplitude A. It's also the distance between the midline and the lowest point on the function. So like the whole height of the function from here, the highest point, down to the lowest point, that's 2 times A. So amplitude tells you how far the function can get from the midline. So for example, if the amplitude was 5, that means that the highest point on the function would be 5 units above the midline, and the lowest point on the function would be 5 units below the midline, meaning that the whole height of the function, the range of the function, would be 10 units tall. Now, period represents how wide a single chunk, a single repetition of the function is. So for example, the sine function is made up of a bunch of chunks that all look like this S shape. They bump up once to come back to the midline, bump down once, come back to the midline. And then that shape just repeats forever. We call this one period of the function. So the width of this on the x-axis is the period. Oh, period. Let me write that on the other side so it doesn't crash up against the definition there. So that's the period. Now, finally, phase shift is the only thing we haven't talked about yet. And the idea of phase shift is just that if you have some non-zero c value there, that's going to cause the function, the whole function, to be translated left or right. Obviously, like as usual, it will be translated to the right if c is a negative number, and translate to, or like if there's a subtraction there, and translate to the left if it's an addition. But you have to divide that c value by b to find out how much the phase shift actually is. Phase shift, though, you could think of as specifically you could think of this, at least for the sine function, as like the starting point, this point right here. And it's the x coordinate of that starting point is the phase shift. So this is c over b over here. Because you could assume that the function, maybe the function doesn't quite start where it's supposed to because of that c value. Like if c is 0, the function starts, the y-axis would be right up against that starting point, right? This would be your axes if c was 0. But if c was not 0, then there would be some shift where you've shifted the function to the right a little bit. And so the function is going to start at a different place. But if you look for that starting point where it hits the midline coming from the bottom going to the top, that point will be c over d over b units from the y-axis. I'll give you an example here on Desmos, just so it's a little easier to tell what I'm talking about. So, for example, here's just the sine of x, right? This is what the function looks like. It's this nice infinite wavy curvy function. If you look close to the y-axis here, you can see that it starts at the midline, right? The midline here is 0, y equals 0. And you can see that it starts at this specific point at the midline right as it's coming up from a low bump and going into a high bump, right? So you can think of this region here starting at this point at 0, 0 and ending here at 2 pi 0 as a single period of the sine function, right? And so the period of this, notice, would be 2 pi units because it goes from 0 to 2 pi in the space of time it takes for it to bump up and down once. So we said that's the period is 2 pi. Now, if I mess with that, let's say I put a 2 in front of the x here. Suddenly, my function is moving a lot faster because I've doubled all my x values, so the whole function evaluates, it changes value much more quickly now. And notice that now that point at the end of our first period has moved from 2 pi all the way over to pi, meaning the period of this is just pi, which makes sense with our formula from before because this b value of 2 means our period is 2 pi divided by 2, which equals pi. Now, let's say instead of having a b value here, I won't have a b value, but what if I add pi over here? Notice that my function doesn't start in the same place it normally does. This is the starting point, right? That same point where it goes from a downward bump to an upward bump is happening not at 0, 0 anymore, but at pi 0. That's because my phase shift on this function is pi. Now, I wish it could be that simple that this number you add or subtract is just the phase shift, but really, if you look closely here, the phase shift is negative pi, because back from our formula, it's supposed to be a subtraction here, right? And so if it's supposed to be a subtraction, but what you see is an addition, then you've actually subtracted a negative number, right? So that's already complicated. Really, our starting point wasn't here after all. It was back here. It shifted to the left by pi units, right? But it looks the same as if it shifted to the right by pi units. Now, to further confuse things, let's put that 2 back. Now, my phase shift is pi by pi over 2 instead of by pi. Because again, as I said before, if we look at our standard form equation, which I guess I can just write here, it's a sine of bx minus c plus d, right? This plus pi is our minus c, so c must be negative pi. And this 2 is our b value, right? And so to calculate our phase shift, which is the location of our starting point, the x location of our starting point, I said we do b divided by c. So that's over here. B divided by, c divided by b. I am losing it today. C divided by b is phase shift. And so when we do negative pi divided by 2, which is our c and our b, we get the x coordinate of our starting point, which, as I showed you, is negative pi over 2, which is right here. So this is how we would evaluate in general. I wanted to show in general what all these terms mean. Phase shift, I know, is by far the hardest one to understand. But let's do some practice problems, and I think that this will start to make a little more sense. So this first one, there's no phase shift and there's no messing with the midline. So the midline for all of these is 0 because there's no plus d at the end, so it's like a plus 0. So they just want us to determine the period and amplitude. We'll do amplitude first and then period. So for all of these, the amplitude is just the number out in front. So for example here, amplitude is 3. Here, amplitude is -5 by the definition in the book. I would call it 5 in this case, but I would accept either one. In general, though, we think of amplitude as a positive number, so I would say amplitude here is 5, and amplitude here is 1/2, right? And this, remember, represents how tall the function can get. So here's an example of if I just take regular x in here. Here, the amplitude is 1 because you can see the highest point on the function goes up to 1. If I change my amplitude to 3, then the highest point on my function now has a y value of 3, and the lowest point has a y value of -3. If I change it to 5, I have to zoom out a little bit to see my y value up here is 5, my y value down here is -5, and if I change it to 1/2, of course, I get a very skinny function, y value of 5, or a very short function, I should say, and a y value of -0.5 here. Sorry, y value of 0.5 and a y value of -0.5 here. Now, going back to the original problems, they also ask us for the period. And so again, the period is not this number. The period is 2 pi divided by this number. So I'm going to say here, b equals pi over 4, but that's not our answer. I'm going to label the b value for each of these. B here is 3 pi, since that's what's being multiplied by the x. And b over here is 1/3, since x times 1/3 is x over 3. So now, given all of that, we can determine our period, which is often abbreviated with the letter p. That's 2 pi over b, right? So in this case, it's 2 pi over pi over 4. Dividing by pi over 4 is like multiplying by 4 over pi. So this is 2 pi times 4 over pi. The pi's cancel. 2 times 4 equals 8. So our period here is 8. Say equals p again, just to make it a little clearer. So our period is 8. So if I actually graph this, what you'll see is one full sine curve, which is like one full period of the sine, which looks like this. It's this S shape where it goes up once and then down once and comes back. That will take 8 units exactly on our graph. So our function here is 3 sine pi over 4. 3 sine, pi over 4x, I should say. And what you'll see here, again, our maximum value is going to be 3. Our minimum value is going to be 3 because our amplitude is 3 and our midline is here at 0. But then what I was saying, we're going to have the whole function, this sine curve, notice that it does a full repetition of its shape. That is, it goes up from the midline, down to the midline, down to the minimum, and then back up in exactly 8 units. And of course, it repeats this all the time, but every time it does it, it takes 8 units to repeat that shape. So we go 8, 16, this will be 24, etc. So that's what it means for the period to be 8, is that this S shape happens in exactly 8 units. It also just means any point on the graph repeats every 8 units. So this is at 2, 3, at 2, 11, or sorry, at 10, 3, I should say, at 2, 3, and 10, 3, we have the same point here at the peak. Here at 6, negative 3, we have a point, and so at the base, and so we'll have that same minimum point over here 8 units after 6 at 14. So that's what it means for the period to be 8. It means it takes 8 units for the whole thing to repeat again. So again, let's very quickly calculate these periods. Like I said here, b is 3 pi for the second one, and so to calculate the period, we would do 2 pi over b, which is 2 pi over 3 pi, which simplifies down to 2/3 since the pi's cancel. So if I graphed this, it would take 2/3 of a unit for the entire function to repeat itself. So this would be a very fast moving function. And then here, b is 1/3. Ignore this. b is 1/3. So p equals 2 pi divided by 1/3. Dividing by 1/3 is the same as multiplying by 3 over 1. And so that's 6 pi. So the period here would be 6 pi units. So the function would be 6 pi units wide per each repetition. So that's the general idea of how period and amplitude work. They represent sort of the height and the width of a single section of the graph. And then the phase shift and the midline represent some other shifts. So the midline here represents a vertical shift of the whole graph. So the midlines are easy here. This is the midline. Here the midline is 0 because there's nothing being added or subtracted at the end. Here the midline is also 0, and here the midline is 4. So those are easy. The harder part is the phase shift. And notice they say the direction and magnitude of the phase shift, of the phase and vertical shift, as well as the midline. The reason, I don't know why they say and vertical shift as well as the midline. The vertical shift is the midline. So the standard is for midline to be 0. So if you ever have a vertical shift like -2 or +4 at the end, that tells you what your new midline is too. If you have a vertical shift of 2 units down, that means your midline is at -2, is at y equals -2. If you have a shift like here of 4 units up, then your midline is at y equals 4. I think that's just what they kind of wanted you to identify here. But the direction and magnitudes of the phase shift is basically saying, are we shifting pi over 6 units to the right or to the left here? Here, c equals negative pi over 6, right? Because again, from our formula, this is supposed to be a subtraction. So if you see an addition, that means that the number you were subtracting was a negative number, which is why it canceled out to addition. B here is 1, since we just have an x here, there's nothing in front of it. And so our phase shift, which is, I'll write phase shift. Phase shift, remember I said is c over b. So that's negative pi over 6 all over 1, which is just negative pi over 6. So we have a shift. Our phase shift, you can say it's negative pi over 6, or you can say it's pi over 6 units to the left. Because when we calculate it as a number like this, like here, it's an addition, so we know it's going to go to the left. But when you calculate it as a number, it turns it negative, and that also tells you that it's going to the left. So a positive in the actual function means the phase shift itself is negative, means you're shifting left. A negative in the function means that the phase shift is shifting right, because it means the phase shift when you calculate it is going to be a positive number. All right, we'll do the same thing for B and C and D. So here again, this doesn't matter. This is just amplitude, so it isn't going to affect phase shift at all. So C here equals pi over 3. Notice it's positive pi over 3 because this is supposed to be a subtraction. B here is 1 again. So C over B, again dividing by 1, so we just get pi over 3, meaning our phase shift is pi over 3 units right. I know we're used to horizontal transformations not matching the sign. It doesn't match the sign of what you see in the function. It will match the sign of the number you calculate when you do C over B. If that makes sense. As long as you remember to switch the sign when you translate this into your C value. Over here, our C value is 0, so right off the bat, I already know phase shift is 0. Because there's nothing being added or subtracted here, it doesn't matter what B is, our phase shift is 0. So this function will start at the correct starting place. And over here, C is again negative 5 pi over 3, because again, this is supposed to be a subtraction, so if you see an addition, it's because there was a negative number there. B here is 1/2, since x over 2 is the same as 1/2 times x. So to do C over B, we do negative 5 pi over 3 divided by 1/2. Dividing by 1/2 is the same as multiplying by 2 over 1. So we get negative 10 pi over 3. Again, dividing by 1/2 is the same as multiplying by 2 over 1 by its reciprocal, and so that's how I got negative 10 pi over 3. So our phase shift is 10 pi over 3 units left. Again, this tells us it's a left, and this being negative tells us it's a left. And that's all for the worksheet. So again, I'm going to bring us back to our standard form definition here so that we can see it one more time. Our standard form, and this is for sine and cosine, so if you wanted to have the standard form for cosine, it should just say cos here. The only difference is that for cosine, the function's starting and ending point look different. So like one period of sine looks like this, where you start at the midline, you go to your maximum, you go back to the midline, you go to your minimum, you go back to the midline. For cosine, it looks like You start at the maximum, you go down to the midline, down to the minimum, up to the midline, and up to the maximum. So the difference between that, basically, this is your starting point for sine, but your starting point for cosine is here at the top. So that's important for understanding phase shift, because phase shift tells you what the x coordinate of that starting point is. We'll do some more practice with actually graphing these in another lesson. We'll do that on Friday, but I wanted to make sure that I got this out to you today so that you all had a chance to sort of see this. Thank you so much. Have a wonderful day.